Oh, no, I love that. Yeah. Okay, let's get going. Hopefully we're recording here. Yes, good. All right, so to start off with, let's talk a bit about the homework. Somehow when I uploaded the HTML file for this, it didn't work, so I'll have to do that after class. But just to talk a little bit about the problems. So the first was on census data about wages. This happened to be in the state of Virginia, although it didn't tell you that. What? You had a pool going on what state it was? Yeah. But I was zooming. Good. All right. So drawing from the prior predictive distribution of a model like that, there's a lot of variables that you have to choose from, but the census was not exactly designed with any particular purpose in mind, so you don't always get the variables that you would exactly prefer. So more often people are using the current population survey to study wages, but the census is certainly more comprehensive. With the census data, you can get as a sample a few percent of the census. They follow up with them with more questions and make that available for researchers. And so that is a very commonly used data set in the social sciences. So if you load that into R, you can get the variables that you want to use just by calling model matrix. That will handle the dropping of the NAs for you, which is not necessarily the best statistical practice, but you would get out a matrix of predictors, and then you can feed that to your stan file, which I will download. Which is a stan. Download. Open. Wages. Okay, so you might have a stan program that looks a little something like this. One thing that people, so a number of things that people ran into problems when doing this that hopefully you managed to get by or overcome yourself. One particularly common and weird problem that a number of people seem to have was thinking that the distribution of the predictors was somehow something that you needed to worry about or draw from or take into account when thinking about your priors, and that is the opposite of true. You know, what we're doing a Bayesian analysis, and I think what the problem text made clear is that you're doing this for the observed data on, you know, years of schooling and age and sex and whatever else that you thought would be a good predictor of wages in the census data. You're taking that data as given, not utilizing any other data, etc. So you don't need to be drawing from the distribution of schooling, whatever that is, because you have in your sample lots of different people, lots of different levels of school, etc. And this is particularly pernicious when you think about, something like the sex variable or race variables or whatever it may be. That is going to be, this is a situation where only people who have wages are included. So it might be like 60% men, 40% women, or something like that. I don't know exactly. You don't have to know exactly. But what does the fact that in any particular state, there's almost an equal proportion of men and women tell you about the coefficient on the women variable? So the fact that it's, 0.55, 0.45, etc., doesn't tell you, anything about, whether women get, paid less, or, if they're paid less for working an equal number of hours, or anything like that. And so what you need to be thinking about your prior beliefs about is the parameters, and particularly the coefficients, the intercept, the standard deviation of the errors, etc., in a model that predicts wages from, years of schooling, gender, age, race, these sorts of things that you might find in the census data. So how would we go about doing something like that? We would pass as arguments each a vector for, the ones that you want to condition on. You could certainly make this more complicated. Number of observations is equal to the number of rows of that vector. First thing I did here was center the variables. We talked about that briefly. It allows you to interpret the intercept as, what do you expect the linear predictor to be for someone who's 0 on all the predictors. So the so-called average person. Of course, sex is a binary variable. So if you average that and you get like 0.41 or something female, that doesn't really correspond to a valid value from its omega, but still you can sort of think of this as the average person, and the conditional distribution of the linear predictor for the average person is, probably not that different from what you might think is the marginal linear predictor, averaging over all people, etc. Another problem that people encounter, which is, I anticipated that you would encounter it. I also anticipated that you would get past this problem more quickly, is that, when you just sort of do this with like normals and whatever, it's easy to get a prediction for wages that is negative, which is impossible. So when modeling wealth, maybe, or certainly negative values of wealth are possible if you owe more or if you have more debt than you have assets. But for wages, it's pretty much impossible to have negative wages, even for grad students. No one is paying anyone else to volunteer. And so one way in which you can get around that, and one way in which the literature in economics overwhelmingly does get around that, is to model the distribution of log wages, which there's a reasonable amount of evidence that is approximately normally distributed, which is to say you're thinking of wages as being log normal. And so here I'm generating the linear predictor, then adding on an error on log wages, and at the end I just return the anti-log of that, and I will get stuff that is strictly positive, making sense for wages. Okay, so if that is the case, I'm thinking about my linear predictor as being on the log scale. What would be a reasonable value for alpha? Again, remembering alpha is sort of the log wage of so-called average person. So you can fiddle around with these until you get sort of a reasonable distribution of predictions, and it turns out an intercept of like 12 on the log scale yields something pretty reasonable. Coefficients on school, on sex, on age, probably going to be on the small side. A 1 year change in schooling or 1 year older is not going to make a huge difference to Log wages, it's fairly well established that women are paid less, so beta 2 would tend to be negative. School probably tends to be positive. Age, if you're doing this linear, probably tends to be a little bit positive. But I'm certainly putting standard deviations on these normal priors that are large relative to the expectation, and consequently, 0 is, definitely a plausible value for each of these betas. Last thing is the standard deviation of the errors on the log scale. So I tend to like the exponential distribution. One thing I don't like about the parameterization of the exponential distribution in Stan is that it takes a rate parameter. So rate is 1 over the expectation. So this prior here reflects the fact that I have a mean, prior mean for sigma of 0.1, which is 1 over 10. Anyway, take alpha, take beta, multiply it by school, take beta 2, multiply by the centered value of school, take beta 2, multiply by the center value of sex, take beta 3, multiplied by the center value of age. Any other predictors that you want to have, that gives you the conditional mean. You can do that as a vector, loop through your n observation, take the conditional mean, add a realization from the error. You get your predictions for log wages. No one actually cares about log wages, so we anti-log that at the end, get a prior predictive distribution of wages. Questions about that so far? Drew? Right. So by taking the mean of each of those variables and subtracting it to make the ones that have underscore at the end of it. So this variable here, school underscore, will have a sample mean of 0. And sex will have a sample mean of 0, and age will have a sample mean of 0. And so alpha, as always, is interpreted as the conditional expectation here of log wages for someone who's 0 on all of the other parameters. So by subtracting the mean to center all of those predictors, instead of interpreting alpha as someone who has an age of 0, so like what is the log wages of a newborn, I'm now interpreting it as the log wages of someone of average age, etc. Yes. So 0.43 doesn't make sense, but it does not change the value of beta 2 in a linear model. It only changes your interpretation of the intercept. So technically speaking, intercept, you should think of it, what's the expected log wages for someone who's average, but that's not that far away from just what's the expectation of log wages over everybody. The marginal distribution has a little bit too much variance. What you should be using a conditional distribution of the average person, but it's not horrible. And so if you sort of think, okay, well, what's like a typical value of wages, the logarithm of that could be like a plausible value for alpha. And so this idea of centering, it's something that RStan-ARM and when we start to learn BRMS are all doing under the hood. It's basically a free way or a free technique to be able better to specify priors on the intercept. It also enables Stan to do better computational performance, better efficiency, better effective sample size, and it basically has no downside. So when you're doing stuff in RStan-ARM, you don't have to center the variables yourself. It'll be done internally. You get the coefficients, they're unaffected by this. RStan-ARM will actually shift the intercept back so it's in uncentered units at the end, but when you specify your prior, if you do so in RStan-ARM, it should be relative to centered covariance. Other questions about that? Christina?
Why does that ascertain interpretation of the
because it is a linear predictor. And so if I did this on school instead of school underscore, I can write chalk. I can write school as school underscore plus average school. So if I do beta school, it's beta this. Yeah. And that piece is in a constant, so it just gets absorbed into alpha. So none of this changes the betas. It does change the alpha, but you can shift the alpha back after you're done if you want. That's what RStanArm does. Anyway, you didn't have to do it in centered predictors, but you want to get in the habit of doing so when you're writing your own stand models. Like I said, RStanArm, BRMS, most Bayesian programs, and honestly, most frequentist programs, etc., are doing this under the hood because it basically has no cost, only benefits. But if you did yours with uncentered predictors, that's fine. As long as you get a somewhat reasonable prior predictive distribution for wages in the end. Now, you can try to do something where you, instead of first predicting log wages and then anti-logging it, predict wages directly. That would be fine. I think that's a harder way to come up with a reasonable distribution. And you also are going to tend to run into the problem that some of your predictions may be negative, which is not reasonable. But it can be done on raw positive wages if you have small enough errors and tight enough priors and things like that. Other questions? Nathan, number one.
So your alpha here at log wages is just because you decided that you were going to model your distributions based on log wages. And so that's why you can then exponentiate whatever you receive.
Yeah.
Okay.
So this is technically assuming wages are log normal or log wages are normal. That's equivalent statements.
And it doesn't really matter. Well, it does matter, but like say you're off, when you then introduce the data, that will be adjusted accordingly.
Right. So this is my prior beliefs about what the wages will look like when I condition on wild data. The posterior distributions of alpha, all the betas and sigmas are going to move. And if you're conditioning on 50,000 observations, it's probably not going to matter very much what distributions you used for the priors here, as long as they're not absolutely crazy. Or, you forget to anti-log at the end and you get negative wages or something, which would be crazy. But if you're doing more complicated models, even 50,000 observations isn't going to eliminate the influence of the prior. So you have to get in the habit of thinking about these things, using predictions of observables to help you check whether your priors are on unknowns are reasonable or not. And I had to, play around with this a few times in order to get something that was kind of reasonable. I can't show you that plot, but or I will when I upload this after. But anyway, you expose it to R. You draw a realization from wages underscore RNG, giving it the predictor variables that you specify, and then you can make a density plot, of that. This one, I could draw it, this is wages. So, it looks something like that. Maybe not like that. But it was a long tail, and, there was a little bit of probability of something like 1 million, which is a huge amount of wages. Maybe very expensive lawyers or something like that. Most of the people who are earning a lot of money have it through capital gains or dividends or stuff like that. But wages and salaries, a couple 100,000 certainly happens for 1 or 2% of people, but getting way out into 500,000, 1 million, certainly something that is very rare but not impossible. So your predictions should be putting a little bit of prior probability on that. Andres? I certainly can.
in the line where you say vector and log wages, you're creating an empty vector, right?
Yeah, so they fill it with NaN or NAs to start with.
And how do you know the loop is going to create something that's going to be like in the log wage, in the log scale, so that when you exponentiate, makes kind of sense?
Right. So that, well, you know, you're exponentiating. So whatever goes into that is going to be exponentiated. Whether that's reasonable or not depends on mostly what are the prior values that you use for these. So a log wage of 12, I think it's like 45,000, something like that. So, you know, that may kind of sound in the right ballpark for average wages among people who work. Similarly, you know, pretty small values on these. So even people who are old are not being, you know, predicted to be millionaires, etc. So, you know, these prior values that you use, you need to keep in mind, okay, these are the coefficients of these predictors on log wages. So you can sort of think about them in percentage terms and stuff like that. So that is really the answer to your question, why log wages is reasonable, you know, once we fill it in with the error, and consequently anti-log of log wages or wages is, you know, roughly reasonable. Rashika. Yes. I'm predicting women will get paid less. Sebastian.
So would you consider these to be informative priors or like informed priors? Or?
Well, they're not stupid priors. I don't think it's particularly controversial to say the more school you have, the better, although not so much. Not controversial these days to say women get paid less. Not controversial to say older people get paid more than younger people. So I didn't use exactly 0 as my center, but I used something that is like within half a standard deviation of 0. So yeah, I would call these weakly informative, but other people who are more accustomed to say, well, you have to put in a standard deviation of like 1 million in order to call it weakly informative, might call these strongly informative. But yeah, I guess that's kind of in the eye of the beholder. That's the number 1.
Not to beat this long, but like, it's perfectly fair game in your priors to just say, I don't really know. I'm just gonna go uniform all the way across.
Uniform on a bounded interval.
Yeah.
That is legal, probably ill-informed, but not, you know, wrong. What a lot of people want to do is say, oh, I have a uniform prior over the entire real line. And that's not a probability distribution. That can't be integrated. It doesn't integrate to 1. So technically that is not a coherent initial set of beliefs to update, although often you're going to get a proper posterior distribution even if you do that. But these days, I'd say that would be considered wrong, although often not harmful. Uniform on a bounded interval, it's a little bit weird to say, okay, you know, the coefficient on women is uniform between 0 and -0.5. You know, basically saying, oh, it's, you know, totally possible that it could be 0.5, as possible as anything else, but 5.1 is impossible. That, you know, usually we think of beliefs as like smooth and not cliff-like. So if you think that you don't know about stuff, that's your prerogative. You often know more than you say. You can often figure out whether your beliefs on the parameters are reasonable by looking at the predictions they imply. But there's certainly nothing wrong with you know, scaling this up by a factor of 10 say, you know, I really don't know if schooling is likely to increase your wages. I'm just paying, you know, $75,000 a year to find out. Your money. Christina.
The normal 0 sigma.
Uh-huh.
That's for the residual.
For the error term, yeah, realization of the error.
So why does the variance of the error term?
It doesn't have to, but that was my prior. Again, the exponential distribution is the maximum entropy distribution for a given mean. So if you're willing to specify the mean and nothing else, except for the fact it has to be positive because it's a standard deviation, then it is the maximum entropy prior. And so that is not too controversial either, although you could disagree with my choice of 1/10 as the mean. You could disagree with my choice of the exponential as well, but it's not crazy. Shu?
What is the distribution?
So that comes out in the R. Wait, that's the wrong thing? No, that's the right thing. Where'd it go? Yeah, this plot. You can't see it, but you can see the code for it. But basically, I took something that was normal around mu and then anti-logged it. So the anti-log transformation always tend to make a longer right tail than a left tail.
Like 10 in like e to the 9 to e to the 10 is a much bigger jump than
E to the 2 to e to the 3.
e to the 8.
Is there a way to create like that right long right tail, like through other like shape like?
You could use gamma distribution for wages. It's not too dissimilar from a log normal, but it's a little bit harder to think about than a log normal distribution. You could use Pareto. Pareto has a really long tail, and that is maybe too long for wages, but a lot of people use the Pareto distribution for wealth, where the heaviness of the tail is even more extreme in advanced countries. Stephanie?
Have you come up with the actual numbers for beta 3? Like, what was your process?
I thought small, but I wanted to make sure that the center of it was on what I thought to be the right side of 0. So young people get paid less. Women get paid less. People who go to school, unless they're in a PhD program, get paid more. You know, I anticipate that would hold in every state because it seems to hold in every state that I know of. All right, moving on. So you can get a plot of that. Given the predictors in the model, I didn't put very many of them, and I didn't have, you know, any specific measure of how good you are at your job. That's not really included in the census. And so I thought a prior mode of about a quarter would be appropriate. Explain maybe 25% of the variability in wages with age, gender, schooling. Could have been something else, even for this model. Could have certainly been something different if you estimated a different model. There's some questions on Piazza, like, you know, how would I pick this? You know, it depends on what model you're estimating, but you could certainly read like any random issue of a microeconomics journal, and it would probably give you a start. Wages is not something that is, you know, esoteric among economists. Posterior median of wages implied by the model. This is the median over people, but you have an entire posterior distribution of that quantity. So you could do this with stan LM, log wages, whatever your predictors are, prior on the R squared mode, etc. Then get the posterior predictions, which is basically the same process as this. Instead of using your prior draws, you use draws from your posterior, conditional on the data that you observe, plug in mu, draw an error, E to that. Now you have your posterior prediction of wages, and you get that. And then you can get your posterior distribution of the sample median by applying to the posterior predictive distribution, which is going to be S by N, sweep over the rows, so margin equal 1, apply the median function. So M is going to be a vector of length S, in this case, by default 4,000, representing your posterior distribution of median wage in Virginia. It will probably be reasonable with you condition on all this data. Nathan, number 1.
You talk about how stan-lm can, like, we had to very specifically specify the vectors that we were taking in. But in stan-lm, just like regular, you can just put in as much as you want or as little as you want, and it can interpret that appropriately.
Yes, although your prior on the R squared needs to take into account not only how many, but which predictors you are using. But yes, you specify the formula just the way that you would do LM. And that's actually the same for every. I mean,
like in stan code, the way stan-lm works, that you can just pass in. Like, so now we're running, say stan-lm was the stan function that we made. Now we can pass in as many arguments as we want, even though previously we set up for you.
Right. Okay, now I understand better what your question is. The stan-lm function, it inputs a formula like regular LM. And like regular LM under the hood, you don't see this part, but it makes a X matrix. And that X matrix can have as many columns as, you know, there are variables in the formula. And actually, when it goes to do its thing in stan, instead of having vector school, vector sex, vector age, it just says matrix X. And matrix can have, you know, whatever number of rows, whatever number of columns. And it's actually doing like matrix algebra and stuff instead of this scalar algebra stuff. Now, we're going to talk about matrix algebra stuff in the context of Bayesian estimation after spring break. But since we hadn't done it, you know, yet for everybody, you know, wasn't in the class in the fall, I've tried to stay away from actually using matrices and vectors with like multiplication. But that is actually what the stan-lm function is doing, which is why it can take an arbitrary number of observations and predictors. Number of observations should be more than the number of predictors, but anyway. Okay, question about Twitter, or not really about Twitter, but about tweets of Russians who were, you know, part of the people who've been indicted for interfering in the election. So, you know, we'll read the data that NBC scraped somehow from suspended Twitter accounts that have been, you know, associated with the Internet Research Agency thing within the Russian government. So you get the data, and then you can create some variables and, you know, manipulate those in order to get things that you might predict whether a tweet gets retweeted, and if so, how many times. So we can, you know, create binary variables. Does it mention Clinton? Does it mention Trump? Does it mention, you know, Black Lives Matter, or, you know, any other lives matter phrase? Is it a reply to someone else, so that you can get by passing a regular expression? Does the tweet start with the character symbol for @? So regular expressions, the caret thing means starts with @. How many hashtags does it include? Those were separated by commas. So I counted up basically the number of commas in the hashtag column. Same thing with URLs and mentions, etc. I divided followers and friends of the Twitter account by 100 just because a change in, one follower I wouldn't think would have an appreciable effect on the probability that one of their tweets would be retweeted, but 100 followers certainly could. Anyway, estimate a logit model for the binary. Is it retweeted ever or is it never retweeted? All those variables. Specify data equal Russia, family equal binomial. By default, it uses the logit link. QR equal true to get better performance, particularly with the default priors, etc. So you could certainly do something along those lines, perhaps with different variables or polynomials or something like that. Questions? QR decomposition. It's a matrix algebra thing. So we'll have to explain that after spring break. But basically, it doesn't change the interpretation of anything. It just improves the computational performance. Okay. And so then there was a question, how would you demonstrate the effect of, something in a substantively reasonable way? So we can just create a new data set based on the unique observations among the data set that we use. Call posterior limpred with that to get sort of a baseline for the probability of a retweeting. And then you can change the hashtag variable or any of the other ones to add one, more to it. You can get the posterior probability of retweet after making that change. Subtract one for the other to get a change in probability. If you look at this plot, it is small, or the effect seems to be small, like 0.01, something like that. It is not normal. It has a multimodal distribution and things like that. But, it seems that, if you add more hashtags, more likely to be retweeted. Yes?
So if you wanted to, instead of increase hashtag, say not content, how would you do that for your new data?
Right. So with those sorts of things where you it doesn't exactly make sense in this context, but like treatment versus control, what you want to do is you take your data set, make everyone control, predict them. Then switch the data set so everyone is treatment, predict them. Take the difference, and then that is posterior distribution of the average treatment effect for the people that you have. So it turns out mentioning Trump or Clinton actually decreased the chance to be retweeted. But some other things like the Black Lives Matter, that was a lot retweeted, and some of the other ones. Andres.
That unique, right, model frame. The unique thing is, I'm not sure what the effect of that is.
Yeah, let's just take the unique rows. So there's lots of duplicative rows. They were actually different observations. They just had the same values as the predictors. So that, reduced it. I didn't want to crash anybody's computer if they tried to run this code. So it just decreased the number of observations I was predicting for.
My crashes.
Other question. Nathan, number one.
Probably very simple. What is the L a lot? Like after an integer?
Oh, yeah. So that means treat one as an integer rather than a double precision thing. So then there was a question about not just, is it ever retweeted, but how much is it retweeted? So you could do a similar model with stan glm.nb, or you could just update it with family neg binomial and change the outcome variable to the raw retweet count rather than the true false. You can do that. You print out the results. It has a reciprocal dispersion parameter. If that was infinity, that means the Poisson would hold. So Poisson is a limiting case of negative binomial. But in this case, the posterior distribution was far from infinity. In fact, it was pretty close to 0, indicating substantial over-dispersion in something like this. Another way of demonstrating this, probably not the most direct way, but the Poisson implies the conditional mean equal to the conditional variance. And so you could get the predictions, calculate the posterior variance for everybody, and then like plot to see if the posterior variance is similar to the observed number of counts that you observe for this. If so, you would get like a straight line. It was not a straight line. So substantial over dispersion of this and a lot of other things in the social sciences. So Poisson distribution often not the best choice. A couple other things before we move on. The first data set, the census one about Virginia, actually was a sample. Not exactly a simple random sample, but it was a sample. And so it is perhaps reasonable to ask, how much would my estimates be different if I had a different sample of 50,000 people who work in Virginia? And you could go through and try to come up with the answer to that question. And the answer would be so small that it's negligible. So conditional on the parameters, which you don't know, but the conditional distribution of the estimates, like frequentist point estimates, conditional on the parameters, is going to be very concentrated around the true parameters. And so, and that's because like in, you know, even in social science terms, 50,000 is a lot of observations. But all these frequentist sampling things were originally done when, you know, 50 observations would be considered a big sample. And so how much the estimates might bounce around from one sample to the next was maybe a more relevant question to ask. But if you have 50,000 or 500,000 observations or whatever, conditional on the true parameters, which you don't know, the point estimates are not going to deviate from that very much. However, you don't know the true parameters. That's what you're trying to find out. So you're going to have uncertainty about that. You're also going to have considerable uncertainty as to what model for this reasonably complicated process of how much each person gets paid, which model is more reasonable to use. You're going to have a lot of uncertainty about those two things that the frequentist approach doesn't tell you anything about. It just tells you about the uncertainty in the point estimates from one sample to the next, conditional on the true parameters. So it's a sort of not very straightforward way of estimating what the parameters are and what model is the most reasonable for estimating those parameters. But at least in this case, the data was a sample, so you could ask or maybe try to answer this awkward question. For the tweets thing, I think this is a lot more representative of what happens in social science today. Not a sample, but it's something that is, you know, pretty interesting to investigate from a social science perspective. So how many ways is this not a sample? It is not a sample of Russians. You know, the Russians, you know, may very well have different, you know, representation of their political beliefs than these handful of Russians who were recruited by the government to impersonate Americans. So not a sample of from the Russian population. It is not a sample of tweets from the Internet Research Agency people. I couldn't quite tell from the article exactly how NBC collected the data, but it sounded like a very typical data collection strategy in the social sciences, which is to collect all the data that you can with reasonable effort and then stop. Perhaps a reasonable strategy, not a sample. So I don't think this was like all the tweets that people who are paid to be Russian trolls tweeted. But I think it's all the tweets they could get on these people. Again, not a sample. Whoever it was that was retweeting these tweets, not any sense a random sample of Americans. So it's not as if you could really infer about some grander population from all these tweets, even though there was like 200,000 of them. But if you're just willing to say, okay, let me look at these data, no other tweets, no other people, what was going on in these things, what made it more likely to be retweeted by someone who thought this was like another American or something like that, totally fine with Bayesian methods. But again, the frequentist methods are really, saying, well, what would be the distribution of estimates from one sample to the next from some population? And you can kind of estimate that, what that distribution is from a single sample if you have a sample. If you have a pile of observations, it's not telling you about how the point estimates would bounce around from one sample to the next, because you don't have a sample in the first place. So it's not going to tell you about that sampling distribution, even though that's probably not what you really want to know anyway. Like the big question is like, how much did stuff like this, not just Twitter, but Facebook and everything else, influence the last presidential election? And so that is a very historically and maybe futurely specific question, but it's something that social science ought to be able to say something about. Something that you ought to be able to say something about, or, most of you. But even if you're in the mailman school, like we want to hear what you think about, stuff like this. Questions? Shoot. Right. So there's two main distributions used for count. One is the Poisson, which has the somewhat unfortunate and usually not very realistic assumption conditional mean is equal to the conditional variance. Negative binomial is a generalization of that distribution. So Poisson is a special case as the reciprocal overdispersion parameter for the negative binomial distribution approaches infinity. So as that gets closer to, that parameter gets closer to infinity, the negative binomial gets closer to a Poisson. But the negative binomial allows and actually enforces the conditional variance is greater than the conditional mean. And so that is often more appropriate for a lot of the counts that we observe in the social sciences that tend to be like, most of them kind of small, but occasionally one that's very big. And so there's some tweets in this set of data that just got retweeted over and over and over again. And that leads to over dispersion. Another thing is very common in the social science is zero inflation. And we actually saw this, like a count model sort of applies for positive counts, but in the data you observe way more zeros than is consistent with that model. Now, what we did here was not exactly the correct way of handling something like that by doing two separate models. Is it retweeted at all? And if so, how much? But if you combine those into the same stand model, which our stand arm doesn't support, but it's relatively easy to do, then you can estimate what's known as a zero inflated negative binomial model that has extra variation at the high end and extra concentration at zero. And that is usually the more appropriate strategy for things in the social sciences. All right, Sebastian.
We're going to talk about
last week of the semester. Okay, well, you can read the readings on the syllabus early. Okay, so let's see, this knit. So today we want to talk about model diagnostics. Soon? Come on. Damn it. So like I said to a couple responses on Piazza, it's more common with the Bayesian thing than the frequentist thing to look at plots because the answer is really a whole distribution. Come on. 89, where's 89? Because the answer is a whole posterior distribution. Now you can describe the center of that with the mean or the median or whatever, but really the whole distribution reflects your uncertainty. And so it's more common to do diagnostics and to convey your results with plots than with, no, don't go away, pop up. Come on. Allow, yes, done. Try again. Oh, come on. Okay, so I'm an employee of Columbia. Something got taken away was, yeah, whatever. All right. So you know by now not to listen to me. Okay, so the diagnostics that we want to do today are for this model, this data set for political economy risk. We're modeling the black market premium on the exchange rate. So how much a dollar is worth in the local currency if you exchange it with somebody on the street versus if you exchange it at an official government bank or something. So BRB2 intuitively stands for black, I don't know, it's the black market exchange rate, the second measure of this. And I just want to use all the variables that are available, which is not that many, except the name of the country. So this data is just observed at one point in time, I think a long time ago. We only have like 60, 70 observations, something like that. I was pretty skeptical that I would be able to explain much of the variation in the black market exchange rate using these predictors. So my prior mode was only 0.2. I specified a seed, which Stan uses a different random number generator than what R is. And so if you want the posterior draws to come out the same way every time, you need to pass a seed. It's not usually a hugely big deal. The distribution will be pretty much the same even if you don't. But you know, the exact numbers will differ, and that can be kind of annoying when trying to describe it in an inner document. I also specified adapt delta equals 0.8, which is actually the default. That is too small because I wanted you to see this warning. There were 2 divergent transitions after warm-up, and increasing adapt delta above 0.8 would likely help. So then, can I run this? Okay. So that should run. Pretty quickly. And then we have the so-called shinystan package, which does a lot for being able to visualize the posterior draws. And so that pops up as a web app. And I should say all of this in addition to a lot of the papers that we're reading at this point in the semester were written by Jonah Gabri, who was a QMSS student 3 or 4 years ago. And his sons contributed a lot of things to Stan. I believe this was his QMSS thesis was basically this shinystan package. Why are we laughing? Well, I mean, most people write them more with like words. But I mean, it's fine if you want to do something like this too.
If you want to. Don't go ahead.
All right. So the first tab here is diagnose. So you can see a trace plot. We have different colors for the different chains. This looks about fine. You can see some other stuff. But the two red dots here were the location of the intercept when it had a divergent transition. And so sometimes if like just changing a DAP delta doesn't work for you, you need to know like what part of the parameter space Stan was having difficulty with. There's only two, so this is really just kind of a suggestion, but it does tend to say, well, when the intercept is like kind of in the right tail, Stan is having, you know, some trouble with that. If there was more than two, it'd be kind of easier to say, you know, where that is going. You can get, you know, when the divergences occurred, etc. This energy thing is underlying the low BMFI diagnostic, which I did not get a warning about this time. Because that wasn't a problem. But a more visual indication of that is to look whether the level of energy, again, there's a physics analogy here, has the same distribution as the change in energy. So we have overlaid histograms here, and they look pretty similar, which is what you want to happen. So this is not a low Bayesian fraction of missing information problem. If the light blue and the dark blue were separated, that is going to tend to result in low Bayesian fraction of missing information. So you can see stuff about that. You can see some, you know, number of divergences were pretty small, etc. It's taking about 6 steps per MCMC iteration, which is about fine. Again, there's a limit by default, which is 15. If you look at the autocorrelation plots, you can see there's a little bit of positive autocorrelation, but it quickly falls to 0. That's good, although it's pretty typical for a Stan model that is written correctly. You can also go to the PP check tab, which implements a number of posterior predictive checks that were talked about in the reading. So you can predict what the black market exchange rate will be for the observations that you have, compare the distribution of your predictions to the actual distribution across the data in the black market exchange rate. Sebastian.
Are these things compatible? Sorry, is this shiny compatible with Stan things or only Stan?
So you can do posterior predict stuff with shinystan. You just have to feed it your own predictions. So really posterior predict is kind of a R-stan arm thing because it knows what your model was. But if you know what your posterior predictions are and you just give it a matrix that's in by S by N with your posterior predictions, then you can do that. There's an additional argument to launch shinystan where you put in your predictions. You can also make these plots statically. So yes, it's a little bit easier to do, or you have to do less if you use R-stan arm or BRMS, but your own Stan programs, you can and should be evaluating how much the posterior predictions differ from the actual data. So here we have density plots in thin lines. This is, you know, one for like 50 or 30 or something draws from the posterior predictive distribution. The thicker dark blue line is the actual distribution of the black market exchange rate in the data. And you can see it's not horrible, kind of captures the concentration around like -2 pretty well. But there's a second mode over here in the marginal distribution of the actual data that it seems like the model is like not specifically recognizing. That would tend to indicate that there's some omitted predictor from your model that causes a small number of countries to have a very negative black market exchange rate that is not being represented here. So you can click through all that. So here's other plots. So your posterior prediction is capturing the sample mean really well, but it's capturing the sample minimum not so good. Here's what you predict the minimum to be. Here was the actual minimum. And so the predicted minimum is consistently too low. So maybe your model is not doing so good for the lower tail, etc. You can click on estimate and you'll get plots like this. So the blue dot is the posterior median. The red line is a 50% credible interval. The thin-ish gray line is a 90% interval or something like that. This is basically a graphical representation of the same information that comes up when you press or you execute print. A lot of these pretty consistent with 0, but you certainly have one variable. I forget exactly what that variable is, but it's 90% interval is still negative. So it's not like we say that this is statistically significant or anything like that, but we're very sure after conditioning on the data that it has a negative influence on the black market exchange rate, etc. So you can click through all of these. The Bayes plot, which is we call it sometimes in some of the slides that we're not going to get to today. You can create a lot of these same plots programmatically, but when you're just trying to kind of understand the posterior distribution, it can be good to just have something where you can click through all that. There's also various things. One of my personal favorites is the trivariate density. So we'll usually put the value of the log kernel on the z-axis and some variables of interest on the x and the y, and then we can does this work on a Mac? Oh yeah, here we go. Yep. Get bigger. Scroll. No. Stop. Come back. Computer seems to be a little sensitive. Okay, anyway, you can get it to a reasonable size, and then you can turn it around to see 2 or 3 dimensions of the posterior distribution on different variables, etc. You can just take a bivariate view as well. So you can put, let's say, this variable and that variable. Look at the bivariate distribution of those things. Anyway, so we're about out of time today. We'll probably maybe spend a little bit of time at the start of class on Tuesday talking about how to make plots like this with Bayes plot programmatically, so you can include them in knitter documents and stuff like that. Definitely, if you haven't had a chance to already, read the article for today, which is under review at the JRSS, but it's a pretty good example illustration of incorporating these graphical ideas into the Bayesian workflow, which is really important. I mean, a ton of people tell you, you should look at the data, and that's reasonable. It's sort of weird that that has to be said. But yes, you should look at the data. But where the Bayesian thing extends from that, you should look at the data in context of the predictions of your model for that data. That also seems like it shouldn't have to be said, but it's definitely something you should do. It's definitely something that is totally coherent from the Bayesian perspective, and it's something because you don't get distributions of predictions and stuff like that from frequentists or a lot of machine learning things. It's an advantage of the Bayesian approach in order to understand, is this like, where was it? If you just had one thin blue line here, it'd sort of be hard to tell, like, is this close to the data, not close to the data? But when you get a bunch of lines, and I think you can increase the number more, you can sort of see, okay, none of them are really capturing this thing over here. And so I maybe need to go back to the drawing board on how to model something like this. And you can see when you overfit, you can see when you underfit, things like that. Okay, so we'll pick it up on Tuesday, talk about more things that you can do with the results of a Bayesian thing with R-stan arm, etc. We'll be talking about averaging predictions together, also other ways of comparing models next week. All right.
Do you have any questions for
One second.